To begin to take a look at patterns of light acquisition and photosynthesis within ecosystems, we'll start with pelagic systems. Photosynthesis in pelagic, which means open water, ecosystems of lakes and the ocean depend on light availability and phytoplankton biomass. So just how we think about photosynthetic rates are going to be determined by how much leaf area you have and how much light is coming down in a forest, for example. The same thing holds in pelagic systems. If we compare lakes or portions of the water within lakes, light availability tends to be pretty similar, at least on a clear day. And what really determines the amount of photosynthesis that happens within lakes is the pattern of phytoplankton biomass. Here's a remote sensing image, a satellite image of the Great Lakes in North America. So for reference, this would be Lake Michigan, and this would be Lake Erie. If we take a look at Lake Michigan, there's some places where there seems to be a lot more light absorption than the center, and you can really see in Lake Erie that there are parts of Lake Erie that look really green, and these tend to be plankton blooms that happen in the summer. Now for reference, in case you were curious, I grew up right here, which is not far from the shores of Lake Erie, and typically there would be phytoplankton blooms that would happen, especially depending on how much pollution there was and phosphorus input into the lakes. The eastern basin didn't seem to have as much problem with these blooms than the western basin does. And in part, that's because the western basin drains a large agricultural area that puts in a lot of nutrients, and then you have plankton blooms that happen. So the patterns of photosynthesis within Lake Erie are driven in large part by nutrient inputs, which generates lots of plankton during the summer in those regions also. And that determines patterns of photosynthesis within a lake. In contrast, Lake Michigan doesn't quite have the same amount of nutrient inputs that Lake Erie would, and you don't get the large phytoplankton blooms in general like you would in Lake Erie. Now if we take a look at a lake, light declines exponentially in water. The equation that we use to represent this is here. Now I stands for irradiance, and Z is depth. So we start here by saying the amount of irradiance at a given depth is dependent on I sub 0, which is the amount of irradiance at the surface. And then you have a negative exponential equation, which says there's an exponential decline with depth that's dependent on a coefficient, which here is K. And so if we take a look at, we'll use this as depth, so vertical depth, and this will be irradiance, that your irradiance is highest at the surface, so this would be I sub 0, and then you have an exponential decline that looks something like that. So large declines in irradiance initially and not quite as much over time. Now you can fit an equation to this line, and that coefficient is K. And so in some places you'll have a relatively quick decline in irradiance. In other places it might be a little bit flatter. So what generates the declines in irradiance with depth? Well, there are a few factors that affect this rate of light decline. So in this case, within the equation, if K is relatively low, that decline is going to happen slowly. So with depth, you might get an exponential decline in light that looks like this. If K is pretty high, that decline is going to happen fast. And so the irradiance at a given depth is going to be lower where K is high than where it's low. Essentially, this represents the rate of decline of light with depth. And in lakes that are relatively clear, then you get very deep penetration of light. So this is Crater Lake in Oregon, really deep blue waters. You can see very deep into the water. And if you were to dive underneath the water, it would still be light at great depth. In contrast, when you do have a lot of absorption of light, such that in really eutrophic, highly productive, lots of biomass, lots of plankton lakes, that light doesn't penetrate much at all because it's just too soupy. This is another representation of the decline in irradiance with depth. So it's same as what we had drawn before. Irradiance is on the x-axis, depth is on the y. But if you take a look, this is on an exponential scale. So this tick mark is 10 to the negative fifth watts per meter squared. This would be 10 to the negative third. This would be 10 to the negative first. So you're looking at a 10-fold, 100-fold, 1,000-fold, 10,000-fold decline in light. A terrestrial forest, light declines relatively quickly. There's a lot of leaves there, and they absorb a lot of light, such that it doesn't take much depth before there's very little irradiance there. Coastal ocean water has an intermediate decline. If we say that this, looking at this line right here, it might take 200 meters before you reach this point, but in a clear ocean water, you might hit that point at 700 meters, something like that. So you can see that coastal oceans and clear oceans, for example, which might be the clearest water that we have, light can penetrate to great depths, as opposed to coastal oceans, and then lakes might be somewhere in here in the middle, depending on whether we had an example like Lake Erie or Lake Michigan. And then a terrestrial forest, light declines relatively quickly. Now the euphotic zone is a term that we'll use in lakes, and what that means, so where the light is good. So photic is light, U is good, and it's essentially the point where you can actually have net photosynthesis. In a lake, it's considered to be 1% of full sun. So after 99% of the light has been absorbed, then you're at the bottom of the euphotic zone. Below there, you can't really have net photosynthesis. In shallow lakes, light penetrates all the way to the bottom. So the entire lake would be considered within the euphotic zone. So you have a lake, it's relatively shallow. The light decline with depth gets to a point such that even at the bottom, you're greater than 1% of full sun. In deeper lakes, though, you can get to the point where you're going to be below the euphotic zone. So if 1% happens here, you're going to have a portion of the lake where you can't actually have photosynthesis occurring. Part of the reason that understanding euphotic zones is important is that in part determines stratification. Most of the absorbed solar radiation is actually converted to heat and not used in photosynthesis. It's absorbed and then re-radiated as heat. And so where you have a lot of photosynthesis, for example, that's where most of your heat absorption is going to occur. So if you know where your euphotic zone is, you know where most of the heat is going to be absorbed and released to heat the water. Once that happens, you get thermal stratification, so that this becomes a relatively warm layer, and then this would be cold, and then there's not necessarily good mixing between the warm and the cold layers. Now the authors are going to go into more detail about pelagic systems, but one point that they also make that's important is that mixing can determine the pattern of light acquisition. Just like we said, light acquisition can determine some of the patterns of mixing. And this is figure 5.7 that you can take a little bit more time in the book to look at. But essentially what they show are the patterns of the depth at which your euphotic zone happens and the depth at which mixing occurs. And when your euphotic zone is relatively shallow, here's the pattern of productivity. It's within the euphotic zone. But you're going to have mixing below there such that sometimes your biomass is up here and sometimes it gets pulled down below the euphotic zone. So you can have phytoplankton biomass below the euphotic zone if it's relatively shallow compared to the mixing zone. In contrast, when they're relatively equal, the euphotic zone and the mixing zone, most of your productivity happens in the euphotic zone, and most of the phytoplankton get mixed within that zone too, and your patterns of biomass look like that. Lastly, if your euphotic zone is deeper than your mixing zone, then most of the photosynthesis occurs just below the euphotic zone. And there's mixing up above there. And so you have different patterns of photosynthesis and biomass depending on what the mixing is relative to the euphotic.